Synthetic diamonds, production, structure, and identification. Synthetic diamonds, also known as laboratory-grown diamonds, represent one of the most significant advancements in modern materials science and gemology. Over recent decades, their increasing availability in the jewelry and industrial markets has generated both scientific interest and commercial attention. Unlike simulants such as cubic zirconia or moissanite, which merely imitate the appearance of diamond, synthetic diamonds are chemically, physically, and optically identical to natural diamonds. They consist of crystalline carbon arranged in the same cubic lattice structure, resulting in comparable hardness, thermal conductivity, and optical properties. This near identity makes the detection particularly challenging and necessitates advanced analytical methods. The synthesis of diamonds in controlled environments dates back to the mid-20th century, when researchers first succeeded in producing microscopic crystals. However, it was not until the 1990s that technological progress enabled the growth of gem-quality stones suitable for jewelry applications. Today, synthetic diamonds are manufactured globally, with applications spanning cutting tools, electronics, optics, and high-performance coatings, in addition to gemstones. Industrial demand continues to dominate production volume, although the gem market has expanded rapidly due to improvements in crystal size, clarity, and color control. Diamond growth processes. Two primary techniques are used for the production of synthetic diamonds: high-pressure high-temperature, HPHT, synthesis and chemical vapor deposition, CVD. Each method replicates, to varying extents, the natural processes responsible for diamond formation within the Earth's mantle, while offering distinct advantages in terms of scalability, cost, and material properties. High-pressure high-temperature, HPHT, synthesis. The HPHT method simulates the extreme thermodynamic conditions under which natural diamonds form. In this process, a small diamond seed crystal is placed in a high-pressure apparatus along with a carbon source, typically graphite, and a metallic solvent catalyst such as iron, nickel, or cobalt. The system is subjected to pressures exceeding 5 to 6 gigapascals, approximately 870,000 psi, and temperatures in the range of 1300 to 1600 degrees Celsius. Under these conditions, the metal catalyst melts and dissolves the carbon source. Carbon atoms then diffuse through the molten metal and precipitate onto the cooler seed crystal, where they crystallize in the diamond structure. Crystal growth in HPHT systems typically occurs over several days to weeks, depending on the desired size. The resulting crystals often display a combination of cubic and octahedral faces, distinguishing them from the predominantly octahedral morphology of natural diamonds. This difference in growth geometry leads to characteristic internal structures, including sector-dependent growth patterns that can be observed using microscopy and spectroscopic techniques. HPHT-grown diamonds frequently contain inclusions derived from the metallic flux used during synthesis. These inclusions appear dark and opaque under transmitted light but exhibit a metallic luster under reflected illumination. In some cases, the presence of ferromagnetic elements allows such inclusions to be detected using magnetic methods. Additionally, HPHT diamonds may exhibit distinctive fluorescence patterns, often forming cross-shaped distributions corresponding to growth sectors. Some specimens also display phosphorescence, continuing to emit visible light after exposure to ultraviolet radiation. Achieving colorless HPHT diamonds historically posed significant challenges due to the presence of nitrogen impurities, which impart a yellow coloration. Advances in purification techniques and process control have enabled the production of near-colorless and even large, greater than 10-carat, stones. Intentional doping with elements such as boron can produce blue diamonds, while post-growth treatments involving irradiation and annealing can generate pink, red, and other colors. Chemical vapor deposition method. In contrast to HPHT synthesis, chemical vapor deposition offers a fundamentally different approach to diamond growth. The CVD method operates at relatively lower pressures and temperatures, typically around 900 to 1200 degrees Celsius, within a vacuum chamber containing a mixture of hydrogen and a carbon-containing gas such as methane. A high-energy source, commonly microwave plasma, dissociates the gas molecules, generating reactive carbon species that deposit onto a diamond seed substrate. Growth in CVD systems occurs layer by layer, resulting in tabular crystals with relatively uniform thickness. The process often involves multiple growth cycles, during which the crystal is periodically removed and polished to eliminate non-diamond carbon phases such as graphite. Over several weeks, this iterative process yields high-quality diamond plates that can be subsequently cut and polished into gemstones. CVD-grown diamonds frequently exhibit a brown coloration due to lattice defects introduced during growth. However, this coloration can be removed through post-synthesis high-temperature annealing, often using hpHT conditions, resulting in colorless material. As a result, many colorless CVD diamonds available in the market originate from initially brown crystals that have undergone such treatments. From a structural perspective, CVD diamonds differ from hpHT diamonds in their internal features. They typically lack metallic inclusions but may contain non-metallic inclusions such as graphite or other carbonaceous phases. Their growth morphology leads to distinct optical effects, including banded strain patterns observable under polarized light. These patterns arise from variations in lattice distortion during deposition and serve as important diagnostic features. Identification of synthetic diamonds. The identification of synthetic diamonds, particularly distinguishing them from natural counterparts, relies on detecting subtle differences introduced during growth. Despite their identical chemical composition, synthetic diamonds exhibit characteristic markers related to their formation environment. Gemological laboratories employ a combination of optical microscopy, spectroscopy, fluorescence imaging, and advanced analytical tools to identify these features. Color zoning is one of the most informative indicators. In hpHT diamonds, impurities such as nitrogen may be incorporated unevenly, producing geometric zoning patterns aligned with crystal growth sectors. Natural diamonds may also exhibit color zoning, but typically lack the regular geometric symmetry observed in synthetic specimens. CVD diamonds, on the other hand, generally display more uniform coloration, although subtle layering may be present. Strain patterns observed under crossed polarizers provide another key distinction. Natural diamonds often exhibit complex, mosaic-like interference patterns resulting from the intense geological stresses experienced during their formation and transport to the Earth's surface. hpHT diamonds, formed under relatively stable pressure conditions, show minimal or weak strain features. In contrast, CVD diamonds commonly display linear or banded strain patterns corresponding to their layered growth mechanism. Fluorescence behavior under ultraviolet radiation further aids in identification. Synthetic diamonds often fluoresce more strongly under short-wave UV than under long-wave UV, whereas natural diamonds typically show the opposite trend. Moreover, the spatial distribution of fluorescence in synthetic diamonds tends to reflect the growth structure, with hpHT diamonds showing cross-shaped patterns and CVD diamonds exhibiting striated or layered fluorescence. The presence of phosphorescence, particularly long-lived emission after UV excitation, is another feature more commonly associated with synthetic diamonds. The challenge of identification becomes particularly acute in the case of melee diamonds, small stones typically less than 0.2 carats that are traded in large batches. These parcels may contain a mixture of natural and synthetic diamonds, making individual testing impractical. As a result, high-throughput screening technologies, including automated spectroscopic systems, are increasingly employed in the jewelry industry. Applications of synthetic diamonds. Institutions such as the Gemological Institute of America have developed extensive databases of diamond properties and continue to refine analytical techniques for reliable identification. These efforts are essential not only for maintaining consumer confidence but also for ensuring transparency in the marketplace as synthetic diamond production continues to expand. Beyond gemological applications, synthetic diamonds are of immense importance in advanced technologies. Their exceptional hardness, thermal conductivity, and chemical stability make them ideal for cutting and drilling tools, heat spreaders in electronics, optical windows, and quantum devices. In particular, defect-engineered diamonds containing nitrogen vacancy centers are being explored for applications in quantum computing, sensing, and photonics, highlighting the interdisciplinary significance of this material. In conclusion, synthetic diamonds represent a remarkable convergence of chemistry, physics, and engineering. Advances in hpHT and CVD technologies have enabled the production of high-quality diamonds with properties nearly indistinguishable from natural specimens. While this presents challenges for identification, it also opens new opportunities for innovation across multiple industries. Continued research and the development of sophisticated analytical methods will be critical in addressing these challenges and fully realizing the potential of synthetic diamond materials.